Good afternoon, everyone, and thank you for the introduction. I'm Emily Bolt, a Technical Services Manager for Signify, and today we're going to provide an optics and lumen maintenance update. So today we're going to give an update on the following. So we're going to look at Legend O, our optical range, absolute and relative photometry, and lumen maintenance, including updates on the maintenance factor standards. Then we will take questions at the end. So first, a bit about us. At the beginning of 2019, our company implemented our name change from Philips Lighting to Signify. We're the world leaders in lighting, providing lighting for professionals, consumers, and lighting for Internet of Things. Our purpose is to unlock the extraordinary potential of light for brighter lives and better world, bringing innovations to the market like Li-Fi, capable of data transmission 100 times faster than Wi-Fi, and 3D printed luminaires tailored for circular economy. The three key areas of focus are light sources, luminaires, and systems and services. We are the #1 global leader in conventional LED and connected lighting systems and services. 2018 generated revenues of 6.4 billion, so twice of our nearest competitor, 75% from professional lighting segment. 27,000 people are employed in 70 countries, and we're committed to sustainability and on target to achieve carbon neutral by the end of this year. You won't see Signify as a brand in the shops, but we do market the best brands in the world. Philips is our primary brand for lamps and luminaires. In the professional space, the software managing them is Interact. We have around 30 lighting brands, here are just a few. So Philips Hue is the world's #1 smart home brand. Colour Kinetics for architectural lighting and used in lighting many of the world's landmarks, for example, the Empire State Building, Bay Bridge, London Eye. 15 London bridges are the illuminated river project, Gateway to India, and the pyramids. Vari-Light and Strand entertainment lighting. These products are used in theatres by artists big and small, including Iron Maiden, AC/DC, and Kiss, to name but a few. So now let's look at our optical portfolio, Legend Optimise, or Legend O as we like to call it. So Legend O was developed and launched back in 2017, but has continued to grow and been adapted based on our customer needs. It provides a complete range of optics covering all public lighting applications, outstanding and flexible performance, LED optic engines, a future-proof distribution, standard and customised flux and optics solutions. So Legend O offers a unique combination of standardised and customisation. It provides a standard LED engine available across a multitude of luminaires and allows us to provide tailor-made solutions to meet the customer needs. Legend O offers complete optics, so a range fit for any application. It's flexible, allowing standardization over applications with outstanding performance across a wide range of geometries, as well as design parameters, for example, tilt and overhang. Operational and energy efficiency. So standard across key portfolio, it's easy to use, the distribution remains the same after LED upgrades and allows design continuity. It complies with national and European road lighting standards. So let's look at some of the optical distributions available in the portfolio. Legend O offers a variety of lighting distributions to fit different lighting configurations, depending on the application, the user, the lighting criteria, so the level of comfort, so maybe the glare classification and TI, the geometry of the area to be lit, and the beam width. Within this wide optical portfolio, there is compact optic selection available. So if the preference is to limit the variety, i.e. to simplify asset management and operations or maintenance, then we use the compact optical portfolio. So if you have a look at the blue ones, designed with luminance in mind, so our M classifications, and the green colour with illuminance in mind, so for our P classifications or C classifications. Distributions are designed for major and minor roads, for small to large streets, for motorised or mixed traffic, pedestrian streets and paths, parking, squares, parks and roundabouts. They can provide high spacings and minimum energy consumption for renovated or new lighting designs. They can be used in various overhangs and luminaire tilt angle positions. With this diverse optical portfolio, Legend O opens up to the option to optimize the lighting solution according to well-defined and/or project-specific criteria regarding quality, local lighting requirements, matching specific application needs, thereby often improving energy profiles. So these include the full range of Legend O. In the UK, we offer all of these optics in our portfolio and they are already in lighting reality. Again, the blue ones are designed with luminance in mind, so these are for our M class and our traffic routes. And the green colour is with a luminance in, so these are for our P and C classes. This additional flexibility really provides the designer with the option to pick the most energy efficient optic for the exact road geometry and application. Sometimes there's a need for more specific optics, including things like wet roads or a higher level of comfort, so a higher G class, with optics available from G1 to G6. Facial recognition, light trespass prevention, so internal louvers with photometric data, catenary implementation, night preservation, protecting the night sky, and biodiversity preservation, protecting our wildlife. In the UK, we probably look at the comfort versions and backlight versions the most. So it's important to note that the higher the G class in general, you get a reduction in spacing and increase in energy consumption due to the level of comfort of the distribution. So if you're comparing luminaires with no G rating to a luminaire with a G3 rating, for example, then although the comfort level for the user will be better, the energy consumption may increase. So it's important to remember the driver here and specify if a glare classification is required. We also have some other dedicated areas. So for example, we have a symmetrical optics. This is the DS50. This produces a symmetrical pattern of light in a road lantern. It's good for things like heads of cul-de-sacs, car park areas, squares and parks. We have specific pedestrian crossing optics. So these are dedicated to light pedestrian crossings and give a positive contrast required. I'll just mention the railway optics. So these have been designed for platforms, but they're very efficient on footpaths at around 30 to 35 metre spacings. So we have optical distributions that have been designed for luminance classes, so for our M classes. So there's some examples on the slide here. So we have things from extra wide, so a DX is an extra wide optic, a DW is a wide optic, DM is your medium optics, DN is your narrow, and we also have some extra narrow optics. And we have the same for our illuminance classes. So for our P and C classes, again, we have extra wide optics down and narrow optics as seen on the slide. So these optical distributions have been designed for specific needs. So wet roads we don't really use in the UK, but we have a wet road optic if required. Comfort, so the DN33, DM32 and DM33 give a higher G rating, so G4 or G6, so for motorway applications, for example. The DM70 and the DX70 are designed for facial recognition. You need to be a bit careful with these. If you don't want facial recognition, if it's not part of your design, then they're a really good optic for many applications, but the energy efficiency is poor. So they'll cover a lot of applications, but they'll use a lot more lumen to do so. Light trespass prevention, so these provide us with internal louvers with photometric data, so you can model the impact. So we have BL1, which is a limited cutoff, and BL2, which is very sharp cutoff at the back. However, we can also provide external louvers for most luminaires for customers who wish to see a louver fitted. Here are some more distributions for dedicated areas. So again, the most popular are the symmetrical optic, so the DS50, and also we mentioned again the railway ones are sometimes very good on footpaths. And then we have our pedestrian crossing optic, and we also have, so we have the right hand side and the left hand side, and we also have specific optics for tunnels and subways. So we mentioned light trespass prevention, and we're looking at the optical distributions. So they provide greatly reduced light trespass. It's an internal louver that fits into the luminaire. It can be used for retrofit solutions. We have photometry for the calculation, and it also preserves the aesthetic of the luminaire because you can't see it from the outside. And we have a BL1, so that's a limited cutoff, and we have a BL2, which is a sharp cutoff. And using the internal louvers can give a 60 to 90% light reduction on the facade. So the Legend O portfolio is designed to perform, so for all application areas and for a wide range of design parameters. For the whole portfolio of lighting distributions, we have maximum spacings can be increased, covering both renovation and new installations. A higher percentage of schemes can be covered, bringing flexibility in lighting design work. So the beauty of Legend O is now it's in the full range of products. So you can use the same optical distribution in a road and street luminaire or an architectural fitting or a floodlight, giving you flexibility to use the correct lighting distribution and product for the application. It also allows the LED to be upgraded easily using the same optical portfolio to keep up with LED advancements. So we've covered the optical portfolio. It's important now to know how this data is presented. So now we're going to look at the difference between absolute and relative photometry. So photometric data is available in two formats. We have absolute photometry, which does not require the use of separate lumen output for the light source, and relative photometry, which requires the LED package flux to be quoted. Both methods produce the same result. The manufacturer should state the format in which the photometric data is supplied. So absolute photometry for the LED luminaires should be conducted according to the IES LM7908 photometric measurements of solid state lighting products. This is an American standard. Relative photometry should be conducted in accordance to EN 13032-1 2004, light and lighting, measurement and presentation of photometric data of lamps and luminaires. Part 1, measurement and file format following. So this is following the European standard, which is as the UK we would normally work to. The difference between the two types of photometric data is the LOR, or the light output ratio. This is the percentage of light emitted from the light source that makes it out of the luminaire. So traditionally with HID lamp sources, you would measure the flux directly from the lamp itself, and then we measure the flux from the lamp inside the luminaire. And the difference between these two values was expressed as a percentage and was the LOR, or the light output ratio of the luminaire. So typically in HID luminaires, the LOR would be around 0.8 or 80%, meaning 20% of the lamp flux was lost inside the luminaire. It's no different for LEDs. So when we calculate the LOR, we talk about the following. So we talk about the source output. This is the luminous flux emitted from the light source only measured in free air. So we're talking about the flux coming from the lamp or the LED board. The luminaire output is the luminous flux emitted from the luminaire, taking into account any thermal and optical losses. So the LOR is calculated as following. So the light output ratio is the luminaire output divided by the source output. And if you want to work out our luminaire output, it's the source output multiplied by the LOR. So source lumens can be expressed in three different ways. So we have cold source flux. So this is the flux emitted from the LED board when the junction temperature is not at the recommended level. So it's done in flash test circumstances in the first 10 milliseconds of the board being powered. So if you measure only the cold flux, then the LOR has to include both the thermal losses from the luminaire once the board is running at the junction temperature it will be at inside the luminaire, and the optical losses from the lenses and the diffusers. So when you use relative photometry with cold source flux, the LOR includes both the thermal and optical losses. Hot source flux. So this is the flux emitted from the LED board when the junction temperature is at the temperature it will be within the luminaire. So if we measure hot flux, then the LOR includes only the optical losses from the lenses and the diffusers. So when you use relative photometry with hot source flux, the LOR only includes optical losses. So you would expect the LOR percentage for hot source flux to be higher than that of cold source flux. Absolute source flux. So this is where the flux measured is the flux out of the luminaire. So it includes all the thermal and optical losses. So absolute source flux will have an LOR of 1. So LOR in absolute photometry is without any thermal or optical losses, and these are already included in the flux. So here's an example. As you can see, the cold source flux is higher than the hot source flux, and again higher than the absolute source flux. As the source flux reduces, the LOR increases to account for the different losses, but no matter which way you apply this, the system's flux is always the same. This is what you calculate with when you use the photometric file, whether it be an LDT file or an IES file or another format. The LOR is built into the file. So although the flux of the file will show the source flux, the calculation is done using the system's flux. In this case, you could do 3 different calculations, each with a different flux type, and get the same result. So absolute photometry measures very precisely the lumens emitted by a specific luminaire. Luminaires that have been measured using absolute photometry can be identified as having an LOR of 1 or 100%. These lumens are often referred to as systems flux, as these are the lumens emitted from the complete system, including thermal and optical losses. The limitation of absolute photometry is that it's only applicable to the exact luminaire or light source combination tested. Relative photometry can be adjusted to measure light distributions by various lamps with different lumen outputs. The luminaires have been measured using relative photometry can be identified as having an LOR of less than 1. These lumens are often referred to as source flux, as these are the lumens emitted from the LED measured in free air without any thermal or optical losses applied. The advantage of relative photometry is that you can measure the source, and based on the fact that you have known losses, you can apply an LOR to many different variants of the same luminaire. To date, there is no standard that states for LED one type of photometric testing should be done over the other. If relative photometry is used, it will always state the source flux and then apply the relevant LOR for the exact luminaire configuration. The LOR is automatically integrated within the photometric file and is therefore automatically accounted for when using the file to perform a lighting calculation. So let's look at an example. Here we have a 20 LED luminaire with 17 different optics. Each optic has the same source flux. Each optic has the same source flux of 4,900 lumens, but they all have a different LOR. This is what you would expect, as every distribution will have a slightly different losses. So you can see if we apply the LOR, then the system's flux is different for every optic. Sorry, I was just trying to get the point there. So for example, here we have the same source flux for all of these 17 optics. We have different LORs, including optical and thermal losses. And we have the system flux here, which is all different because the system's flux is the source flux multiplied by the LOR. So if we use relative PM data for a 20 LED luminaire and we use the optic 14, the PM and the photometric file will have a flux of 4,900 lumens, which is the source flux. The LOR of 90.6 is applied within the photometric file, and the system's flux that is used in your lighting calculation is 4,439 lumens. This is all done in the photometric data file, so the IES or LDT file. You don't have to account for this. Here you can see that the LOR for relative PM data is 90.6. So here, the photometric file is used in the calculation for lighting reality. It gives you the following results. So we need 4.9 kilolumens here, and it gives us an EAV of 5.96 here and an EMIN of 1.46 here. So if we look at absolute photometry and we take the same example for optic 14, the photometric file will have a flux of 4439, which is the system's flux. The LOR is 1, as this is absolute photometry. Therefore, the source flux and the system's flux are the same. Here you can see that the case for absolute photometry, the LOR is 1, and this is used in the calculation in lighting reality, and it gives the following results. So this flux now, the system's flux is 4.439 kilolumens, and we've got an EAV of 5.96 and an EMIN of 1.46, which is exactly the same. It's also important to understand what type of photometry you are using when you calculate the efficacy of a source or luminaire. So luminous efficacy is a measure of how well a light source produces visible light. It is the ratio of luminous flux to power measured in lumens per watt in the International System of Units. So the source efficacy, or lumens per watt, is equal to the source lumens divided by the circuit watts. Source lumens are the lumens from the lamp or LED module. Luminaire efficacy is a term normally used to describe the performance of a lighting system where the input and the output values differ. The efficacy of a light source is given by the luminous flux it emits divided by the power consumed and is expressed in lumens per watt. Lumens, so we have luminaire efficacy is equal to the source lumens times the LOR divided by the circuit watts for luminaire efficacy. Luminaire lumens are often referred to as systems lumens, the lumens from the luminaire including all thermal and optical losses. So let's look at another example using the same 20 LED luminaire with 17 different optics. Each has the same source flux, so we have 4,900, but they all have a different LOR. This is what you would expect, as every distribution will have a slightly different losses. So you can see here, if we apply the LOR, then the system's flux is different for every single optic. They all have the same system power, so they're all 33 watts, but they all have different efficacies. So if we take this example using relative photometry, we have 20 LED using optic 14. The source wattage of the lamp of the LED module is 28 watts and the luminaire wattage is 33 watts. So the source flux is 4,900 lumens with an LOR of 90.6. So if we look at the source efficacy, then you would have the source lumens, which is 4,900 lumens, divided by the source wattage, which is 28 watts, which will give you a source efficacy of 175 lumens per watt. If we calculate the luminaire efficacy, we have to use the source flux, 4,900 lumens, multiplied by the LOR of 0.9. So this gives us 4,436 lumens. We then divide this by the luminaire wattage, which is 33 watts, which gives us a system efficacy or luminaire efficacy of 134 lumens per watt. With absolute photometry, then the data, we are only calculating the luminaire efficacy. So if we take this example using absolute photometry for the same 20 LED luminaire and optic 14, then we only use the luminaire wattage, which is 33 watts. To calculate the luminaire efficacy, we have used the system flux, so that's 4,436 lumens, multiplied by the LOR, which is 1, so that gives us our 4,436 lumens. We then divide this by the luminaire wattage, which is 33 watts, and this gives us our system efficacy or luminaire efficacy of 134 lumens per watt. Again, it gives you the same result. So sometimes if you quoted a very high efficacy, for example, if someone quoted you 175 lumens per watt, then this is just the source efficacy, not the luminaire efficacy. So to summarize, we have relative photometry. It requires the LED package flux to be quoted, so talks about source flux. The source flux will be quoted and then you apply the relevant LOR for the exact luminaire configuration. The LOR is automatically integrated within the photometric file and is therefore automatically accounted for when you use the file to perform a lighting calculation. Absolute photometry measures very precisely the lumens emitted by a specific luminaire. Luminaires that have been measured using absolute photometry can be identified as having an LOR of 1 or 100%. These lumens are often referred to as systems flux, as these are the lumens emitted from the complete system, including thermal and optical losses. The limitation of absolute photometry is that it is only applicable for the exact luminaire light source combination tested. There are two ways in which the LED luminaires can produce photometry. There's no standard that states for an LED one type of photometric testing has to be used over the other. Both methods produce the same result, and the manufacturer should state the format in which the photometric data is supplied. So as we've discussed this extract has been taken from the brand new version of BS 5489/1/2020, and it says lighting design can be carried out using absolute or relative photometry as described below. Both have advantages and disadvantages, and there is no preferred option as either method is expected to produce the same result. Whether you are using absolute or relative photometry, it does not change the lighting performance of the design. The results are absolutely the same. So the next topic covers the update on how we calculate maintenance factor, and it gives a little update on Lumen maintenance figures. So in 2019, the CIE released a new document, the ISO CIE TS 22012 Light and Lighting Maintenance Factor Determination Way of Working. This was followed in 2020 by the ILP Guidance Note 1120 Maintenance Factor Determination and its impacts on the performance and overall efficiency of LED luminaires. So we're going to have a quick look at what these documents mean in terms of calculating the maintenance factor in your lighting calculation. So this formula may look familiar to you all. It's how many of us have calculated the maintenance factor for our lighting designs. We've used this formula for our HID luminaires, and we have continued as an industry to adopt this for our LED luminaires. And it was taken from BS 5489/1/2003. This is a new formula for calculating maintenance factors in our lighting design. It looks very similar. It's taken from the Lumen maintenance ISO CIE TS 22012 document and the ILP guidance note 11. So the overall maintenance factor has now changed from MF to FM, and it's determined by the above formula, where FLF is the luminous flux factor, which was your lamp lumen maintenance factor. FS is the survival factor, which was your LSF, so your lamp survival factor. And FLM is the luminaire maintenance factor, which was your luminaire maintenance factor. FSM is new. It's the surface maintenance factor. This is so the same formula can be used for both indoor and outdoor applications. But in outdoor applications, apart from tunnels, this would be ignored, so it would be given a value of 1. So our FLF is the luminous flux factor. It expresses the depreciation of the luminous flux over time due to aging of the light source or luminaire during regular operation. This excludes external factors. This is defined as the ratio of depreciated luminous flux to the initial luminous flux. So our FLF is what used to be our lamp lumen maintenance factor, so our LLMF. So for an HID lamp, this was generally when the lamp hit 80% of its lumen output, and it would be replaced every 3 years, for example. 80% was used as this was the level at the time that it was thought that the reduction of light would be noticeable. With LED, this time frame's changed from 3 years to 50,000 hours and now 100,000 hours. And we started with L90 for some LEDs, and then we went to L80, and for a few years now we've achieved L90. Recently, data has shown that in some cases, L96 to L98 can be achieved. So our FS is the survival factor. So this expresses the probability of the light source and or luminaire to continue to operate in a given time. So this is the same as our LSF, so our lamp survival factor. Throughout the industry, we've always assumed a value of 1 for the LSF due to the fact that once the lamp has failed, a spot replacement will take place and the lamp will be replaced. This hasn't changed, as the new standard states. The spot replacement regime assumes that when a luminaire or light source fail, they are immediately replaced by a luminaire or light source with similar characteristics. In this case, the corresponding survival factor FS is 1. So we use this in our maintenance factor calculation as if the luminaire produced no light, it would be replaced. FLM is the luminaire maintenance factor. It expresses the relative output of the luminaire due to dirt deposited on the light sources, optical components, or other components influencing the luminaire output. This is the same as the old LMF, which we take from the British Standard and base it on the environmental zone and the mounting height and the time between cleaning. So we use table C1 and BS 5489/1/2020. So this is what our new maintenance factor formula looks like for outdoor luminaires. So it's FM equals FLM multiplied by FLF multiplied by FS. Not so different from the old one. Constant light output. So when we talk about constant light output or CLO, this was adopted by the industry as an energy saving technique. It initially dims the light source to the predicted end of life luminous flux and steadily increases the current over time to compensate for the depreciation in luminous flux due to the aging of the light source. The new standard looks at 2 different ways of representing CLO in the maintenance factor calculation. So method 1 is generally how we do it now. You carry out your lighting calculation using the PM data provided by the manufacturer and using a maintenance factor as though no CLO is to be applied. So you design it with an FLF based on the lumen depreciation of the lantern. So for L90 at 100,000 hours, then your FLF would be 0.9 and you use this in your maintenance factor calculation. Most manufacturers now give CLO as standard, so they then take the flux that you've designed with and they apply the CLO at the point of order. The other way to do it would be to use the FLF of 1. Therefore, the luminaire doesn't depreciate as the CLO function maintains the required luminous flux. If you opt to do it this way, please inform the manufacturer at point of order, as in some cases you could end up with a CLO being double counted. So as we said, the preferred method is to use the correct lumen depreciation in your maintenance factor calculation based on the L90 figure. So if your light and reality calculation, you needed 3,900 lumens for a non-CLO. So these are the end-of-life lumens taking into account a lumen depreciation of 10%. Then the manufacturer provides you with a CLO lantern and they calculate the CLO lumens based on the lifetime. So you can see here that 3,900 is what we need in our lighting design, but the CLO value is 3,500 because we've taken the 10% off, we've corrected it for the L90 figure. And this is done at point of order. So what has changed? Very little. The abbreviations have changed, but the definitions have stayed very much the same. And if we plug the figures into the new formula, so for a 6-year clean based on an E3, E4, the values we use in our lighting calculations have remained the same. So this is for a 6 metre or below column, and this is for anything above 6 metres. So recently we've been looking at our lumen maintenance, or our FLF, lamp lumen maintenance factor, to see if we can improve this from L90 for our Legend or portfolio. In 2020, new data was supplied by the LED chip manufacturers that has allowed the revision of lumen maintenance in our luminaires. For the last 5 years, we've given L90 as the lumen maintenance, and this was the worst case. So it meant no matter whichever combination of luminaire size, LED number, or drive current, all our lanterns achieved L90 as a minimum. The new data suggests that in some cases, this may now be increased up to L96 or L98. We have seen this in the market with some of our competitors now claiming much higher LXX values. So when we talk about the FLF of L90, as we said, this was the worst case, and many luminaires would achieve higher than this, for example, L95. When doing a lighting design, to really optimize the solution, we could provide a different LXX value for every combination. So we could say this combination is L90, this is L91, this is L92, this is L95. But this would not be practical, as every time you did an optimization in lighting reality, you'd have to change the maintenance factor in your lighting calculation. You have to also remember that the CLO function is based on the FLF. So the LXX value, the luminaire wattage, is calculated based on the average over life. So as the LXX value increases, then in theory you could see a slight increase in the luminaire wattage, as the average for an L90 product is in a different place to the average of an L98 product. In L98, the impact of CLO is minimal, as the start and end wattage would only be 2% difference, and in a 20-watt lantern this is minimal. Let's look at an example. So here we've done a calculation based on L90 product, giving us an overall maintenance factor of 0.83. So the required flux for that calculation to comply is 3.89 kilolumens. If we plug this into our software, it tells us that the CLO wattage is 22.33 watts, and the CLO lumens are 3,500 lumens. It also tells us this lantern is actually capable of L97 at 100,000 hours. If we redo the same calculation, but we use L96, giving us a maintenance factor of 0.86, so it's increased from 0.83 to 0.86, we now only need 3.75 kilolumens to get the same lighting levels on the ground. So if we plug this into our software, it tells us that the CLO wattage has actually increased to 22.99 watts, and the CLO lumens are 3,600 lumens. So you can see by increasing the LXX we provide due to the CLO function, it will not always improve the energy consumption, as the average energy is much nearer the end-of-life wattage the higher the LXX value. Therefore, although in the background our software is using the improved lumen maintenance to calculate the CLO, we're advising that the LXX value you continue to use for our road and street luminaires will be L90 at 100,000 hours. This will be your FLF used in your maintenance factor calculation of 0.9. So thank you very much for your attention. If there's any questions, I'll be happy to take them now.